Sorry, Pak Ruli.
Oh, udah jalan ya?
2 minggu lagi UTS langsung lah.
Semoga sukses. Kok hilang Pak Asmawi? Gimana Pak Asmawi?
Baik, Prof.
Oh, berarti berdua sama Pak ini?
Basori, Pak
Ya?
Ruli.
Oh, ya kan harus segera lulus kan? Oh, ini ada Pak Ruli juga.
Sore Prof. Jarot.
Oh, sore.
Alhamdulillah. Sehat ya, Prof?
Pak Rudi gimana? Sehat?
Di rumah ini, hujan deras di Bandung.
Oh, sama ini juga pas hujan ini.
Hujan deras sekali, Pak.
Ya, ini. Moga-moga yang penting jangan banjir.
Nah, itu. Kayaknya enggak banjir lah. Hujan angin tadi. Ini barusan aja ini selesai.
Oh. Ya. Ini kita ada Pak Utama juga nih. Selamat sore Pak Utama.
Sore Pak Jarot. Hujan lebat di sini Pak.
Sama-sama.
Bukan main. Pak Rudi Lasmono apa kabar?
Alhamdulillah baik Pak Utama. Sini hujan.
Tempat Bapak hujan juga?
Hujan lebat sama angin Pak.
Oh iya. Ya rezeki Pak.
Amin. Alhamdulillah.
Iya Pak.
Ya tapi sekali-sekali nengok jendela khawatir juga Pak.
Iya.
Lihat pohon, lihat ini, waduh. Ya sekarang udah selesai lah. Mudah-mudahan.
Ada yang batuk ini. Ini Seaborg Denmark ini sangat aktif sekali promosi ke Indonesia. Karena memang marketnya yang diincar adalah Asia Tenggara, PLTN terapungnya.
Prof, ini ada isu kalau di IKN nanti pakai PLTN thorium gimana? Dengar nggak, Prof?
Ya, sih nanti bisa ditanyakan itu ke Seaborg. Saingannya Torkon ini.
Ini isunya santer ini. Kalau thorium itu apa sudah proven sih teknologinya ya?
Mungkin butuh waktu nanti, mungkin si Nicola bisa cerita. Mereka lebih menggunakan uranium duluan. Mungkin tahun 2050-an ke atas baru thorium masuk. Kalau Seaborg itu roadmap-nya seperti itu.
Iya.
Jadi mereka ini pabriknya nanti di Korea. Karena memang shipyard itu kan, tongkang kapal-kapal itu kan banyak kan bikinan Samsung atau mana itu.
Iya. Itu industri besar itu di sana itu.
Ya.
Si Samsung itu.
Ya.
Bukannya Cina, Prof.
Kenapa?
Bukan Cina.
Nggak tahu, negara-negara barat mulai menghindari Cina. Cina jadi saingan mereka. Cina kan mau bangun PLTN terapung juga.
Iya. Tapi saya pernah waktu di Beijing itu saya masuk ke museumnya mulai dia bangun PLTN tahun 1959 itu memang saya lihat foto-fotonya masih hitam putih itu teknologi gotong royong banget itu Cina itu. Civil work-nya itu banyak sekali orangnya. Ya. Dia masih sama Kendu waktu itu.
Oh, Kanada ya?
Ya Kanada. Jadi itu saya fotoin, tapi fotonya dibawa mahasiswa itu. Nggak dikasihkan saya. Jadi step-stepnya itu Indonesia harusnya niru itu gitu ya. Tapi maksud saya, kan dulu Soekarno sudah ngomong tahun 60-an. Itu aja pijakannya. Jadi kalau saya katakan sekarang ngomong energy mix, ya energy mix tanpa PLTN, bukan energy mix itu. Energy mix minus, ya kan? Namanya energy mix ya apa aja energi.
Ya, ini sih Indonesia itu belum keluar dari cangkangnya, masih follower, Pak.
Ya tapi ruwennya harus dirubah itu ruwen itu.
Pak Jarod,
Ya,
bukan kalau floating PLTN itu di atas ponton, flat top bar,
ya,
dan dia berada di satu lokasi.
ya.
Di mana itu? Di laut, di sungai?
Kalau idenya ada di pantai, Pak.
Di pantai. Nah, terus legalnya di pantai itu milik siapa ya?
itu memang masih perlu dipertanyakan, terutama tiap negara kan punya aturan sendiri-sendiri kan.
Saya arahnya bukan dipertanyakan, Pak. Suka dibuat aneh-aneh, Pak. Yang kedua, Pak, yang sesuatu yang floating itu selalu banyak masalah dengan maintenance, Pak. Maintenance untuk maintain flat top barges-nya itu.
Ya.
Biasanya kami kalau yang seagoing itu ada akal-akalnya pada berapa bulan itu dimasukin di sungai di air tawar. Itu binatang yang suka nempel-nempel itu pada rontok, Pak. Sehingga umur maintenance-nya yang mestinya setahun jadi 2 tahun.
Ya, ini pembicaranya udah ada. Halo, Nicola. Dear Nicola, are you there?
Hello. Yes, I'm here.
Okay, thank you.
Good afternoon, everybody.
Good afternoon.
Good afternoon.
Good afternoon, Nikolai.
Are you in Singapore or in Copenhagen or?
I'm in Copenhagen.
Oh, Copenhagen. Okay. I thought you are in Singapore or in Seoul.
No. I'm located in Copenhagen.
Okay. Oh. What time is it today? This time?
It's 10 a.m. So it's
in the morning. Okay.
Yeah. Yes.
Okay. Well, we are still waiting for the chairman of Indonesian Nuclear Society.
No problem.
He will give the opening speech.
Yes.
Already here.
Okay,
Pak
I am
Susilo?
ready.
Are you there? Okay. So, Nicola, every Thursday we have a webinars, our Indonesian Nuclear Society, talking many things, including not only nuclear energy, but also for the medicine, for the agricultures, many things. And we invite not only technical persons, but also sometimes politicians, because nuclear just not only the technical matters, but social politics aspects also. So I hope in December 13 you're okay, is it?
Yes, it is.
Okay.
That's very good. I
Yeah.
tried to reply to your emails, but I got error messages for most of them. But the essence of it is that we are fine on December 13th, and Zoom is good, and we're looking forward to it.
I already received your email.
Good. Yes.
Okay. I think it's very interesting. Our participants want to know about. I used the title, the floating NPP, the Seaborg floating NPP. Maybe some of them interest on
That is That's what it is. Yes.
Okay. Kita mulai ya. I will start soon. Selamat sore, good afternoon, participant of the Indonesian Nuclear Society's webinar. Nicola, I will speak in Bahasa Indonesia first, then I will use the English language. Selamat sore Bapak Ibu sekalian, kita memasuki webinar ke-47 tahun 2022. Jadi ini kita moga-moga sampai minggu terakhir Desember, tapi kita harus off juga karena ada libur Natal tahun baru. Kita hari ini akan mengundang tamu dari jauh, dari Copenhagen, dari Denmark, yang akan bercerita terkait PLTN terapung mereka. Menariknya adalah Denmark itu negara yang tidak punya PLTN, tetapi mereka menawarkan PLTN. Tentu saja Anda, Bapak Ibu semua bisa bertanya nanti bagaimana teknologi mereka, bagaimana kelebihan mereka, dan lain sebagainya. Dear participants, today we have a special speakers from far away from Indonesia, from Denmark, from Copenhagen, Mr. Nicola Agerhammond. I hope my spell is correct, Nicola.
It's perfect.
He will speak about, well, I would like to say floating NPP, because many people, not only small numbers, they are eager to know what is floating NPP. Besides Russia, they have already the floating NPP, maybe China, they are developing also. And now we ask the Seaborg technologies to talk about their nuclear power reactors that I say the Seaborg is a company that's very active in Southeast Asia, promoting their technology. They said that this is suitable for Indonesia, for the island countries. But anyway, before we move to the main agenda, I would like to ask Dr. Susilo Widodo to give the opening speech. Please, Pak Susilo.
Baik, terima kasih Pak Jarod. Thank you very much, Dr. Jarod. Good evening, selamat sore. Assalamualaikum warahmatullahi wabarakatuh. Salam sehat, salam sejahtera untuk kita semua. Shall I speak in English or in Indonesia, Pak Jarod?
You will. I think it is better in English because
my vocab is very limited. So let me first of all would like to thank to God to give opportunity for us to meet again in this meeting, because this is the routine meeting every week. And as Pak Jarod mentioned, Dr. Jarod mentioned that. Today is in the 47th meeting in this year, so almost every week. Maybe we will reach 50 meeting on this year. On behalf of Indonesian Nuclear Society, I would like to thanks to Mr. Nicola Agerhammond for your time, for your willingness to share your experiment, what your and others to us. And yes, I heard from this flyer of this meeting that you might share to us about the floating nuclear power plant. And so we know that there are one nuclear power plant, floating nuclear power plant in Russia, in the academic Lomonosov, Russia. And well, I know well that Denmark also developed high tech play important role in developing high technology. and as well and also including the might be nuclear power plant as well. And I know some researchers in Denmark, and when I worked in Europe, and at least your city is very nice in Copenhagen, and I like very much with the subway track in Copenhagen, because the rule is like cave, yeah, and there's many ornament and so on. Oh, very like, oh, this would be nice if we can make a similar cave type subway track in Jakarta. And please you note that in case you offer some kind of nuclear power plant, floating nuclear power plant, we might make cooperation so the local content of this some kind of this nuclear power plant will be, well, could be, might be 50-50, because we have a big company on the ship company called PT PAL, what is English PT PAL, in Surabaya. And PT PAL is has a capability to make a big ship for floating power plant, and maybe they already have cooperation with the company in Turkey to such project also. So it will be interesting for us to hear from you about the possibility to build a floating nuclear plant in Indonesia, because we have consist of many islands. We have 17,000 islands, and we need every island need not so big installation. So maybe the floating nuclear power plant will be very appropriate to supply electricity in some island, especially in eastern part of Indonesia. Well, this is all what I would like to say, Pak Jarod. The participant has already increased up to 144, and I would like to end my speak. Thank you very much, and thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Pak Susilo Widodo, he had been in Vienna as the CTBTO officer for about how many years? 8 years, yeah, Pak Susilo. So
9
he
years.
knows about Europe. So I would like to show the short video clip about the Indonesian Nuclear Society, and inviting everyone that is not the member to join our Indonesian Nuclear Society. Okay, let's move to the main agenda. I would like to introduce Mr. Nicola Agerhammer. He worked for the Seaborg, based in Copenhagen. It is very interesting. Your background is the finance and strategic management, your educational background, and you are already worked well international community in Brazil, in Panama, and other countries also, and you have experience on the offshore wind energy also. So it is, yeah, well, it's very, very colorful, I say. But anyway, please, you have a time about 40 or 50 minutes. After that, we can discuss many things about your technology. Please, Nikolai.
Fantastic. Thank you very much, Mr. Jarrett, for giving me this opportunity to speak, and thank you to the Nuclear Society of Indonesia to allow me to present myself and Seaborg and our proposed technology. So as Jarrett says, I have a background in economics. I spent 10 years in the renewables industry and now work as a head of business development for Seaborg. So it is my team's responsibility to commercialize the floating nuclear power plant that we are developing in Seaborg. I will just share a few slides to support my presentation. I hope you can see the slides now. Otherwise, yeah. I'm sure Jared will let me know. Good. Yeah. So jumping straight into it, Seaborg is a company that was founded back in 2014 by a group of Danish scientists and nuclear engineers. We have ever since been privately funded and are therefore also still privately held. That means that we are fully independent of states and other organizations and can therefore freely operate in, for example, Indonesia. We are at this time around 120 employees, and we have team members from 25 different countries, among those Indonesia. Our main office is in Copenhagen, Denmark, as already mentioned, but we also have offices in South Korea and Singapore. The South Korean office is particularly active in dealing with our partners. We are partnering both with Samsung Heavy Industries in South Korea as one of the leading shipyards in the world, and we are working together with Korea Hydro and Nuclear Power as one of the leading nuclear operators in the world. Together with those two partners, we are jointly developing our floating nuclear power plant technology. And our technology, we call it a compact molten salt reactor. So that is what you see here on the top left. That is a relatively small in size nuclear reactor utilizing molten salt, so salt that is heated to a liquid state in which the uranium is dissolved. And therefore the salt is both the fuel and the heat transfer medium. I'll get back to what the point of that is, but that is the concept. It's, as said, relatively small in size, but also relatively powerful in impact. So each reactor can produce 250 megawatts thermal energy continuously, and that translates to around 100 megawatts electrical per reactor. The way we envision to bring this to the market is in the form of a barge shown in the bottom of this slide. So the smallest barge will hold 2 reactors, delivering 200 megawatt electrical, and the largest of the barges that we envision will be having 8 modules, so in total delivering 800 megawatt electrical output. The benefit of the barge is both the flexibility of deployment, the ease of towing it to a site, but it's also a matter of utilizing the benefits of mass production, so scale efficiencies, utilizing already established supply chains, among others in the shipping industry, so from the shipyards. The obvious benefit of a nuclear reactor relative to some of our renewable colleagues is that we have a very high capacity factor. We are not dependent on the weather conditions to generate energy. To the contrary, we are very independent and can produce at a very high continuous output. The compact molten salt reactor is particularly interesting because of the use of salt. Salt is a nice product to have in a nuclear reactor because it is solid as a rock when it goes below 500 degrees centigrade roundabout, and it only boils at a temperature that is way beyond the feasible temperature of the reactor. That means that you have a liquid in all operational scenarios, and that is good because then you don't have high pressure as you know it from conventional nuclear, and therefore you are dramatically reducing the maximum credible incident. In addition to that, the chemistry of the salt means that the vast majority of fission products coming out of the nuclear reaction will be retained in the salt. So should an accident happen, any release of material from the reactor core will be, the fission products will be retained in the salt, which will quickly crystallize and become this rock-like structure. So the safety profile of a molten salt reactor is attractive, we believe, for large-scale deployment of nuclear. And all in all, a molten salt reactor falls into this concept of advanced nuclear reactors. And we then deploy that on a vessel, why Jared called us a floating nuclear power plant, which I believe is an appropriate categorization. Molten salt reactors are not new as a concept. As many of you are probably aware, already back in the 1950s, the Americans were making experiments with molten salt reactors. The Oak Ridge National Lab in the United States of America were running a series of tests on molten salt reactors, one of which in the 60s ran for multiple years, showing stable and very good properties as a nuclear reactor method. For many reasons, the American research project was closed down, and for other reasons, it was never really commercialized. As you may know, the Chinese have since picked it up and have developed their own molten salt reactor concept, but it's one that is not widely known of. So we are building on the American experiences, but still there are many years of knowledge and experience that we can build on. So we are not inventing the nuclear reactor itself from scratch. That is actually building on relatively old and therefore also solid American experiments. But the main reason for the lack of commercialization, we believe to have found, was the use of graphite as the moderator in the reactor core. So the Oak Ridge experiments were built up around a reactor core where the graphite was inside the core and acting as a moderator. That poses two challenges as we see it. One, the graphite is a relatively poor moderator, meaning that you need quite a lot of graphite to have an effective reactor or a critical reactor. That makes it relatively spacious in terms of relative to the output, which has its disadvantages. The second part of the graphite is that under irradiation, it was observed to start cracking, which means that it's not stable for very long as a moderator. And therefore, we believe that it comes with some economical disadvantages because you need to exchange the reactor core at a frequency we think is too high. So what Seaborg has done is that we have invented a proprietary moderator so we can leave out the graphite from the reactor core. And since we are using a significantly more effective moderator, we are also allowing for a very compact design. So what is that moderator? But that moderator is natrium hydroxide. So that is a salt. It's known in many parts of the world as drain cleaner. Natrium hydroxide mixed with water is commercialized as a drain cleaner in many countries around the world. It's a byproduct from the chlorine industry. So it is available in abundance and at a very reasonable price. And the way we utilize this moderator is as shown at the top left-hand corner of the slide here. So our reactor core, imagine that this is a cross-sectional cut of the reactor. So we have steel tubes within which we have the fuel salt, so the salt containing the uranium. And then around those fuel tubes, we will have the natrium hydroxide acting as the moderator. All in all, this allows for a critical nuclear process or fission process inside the reactor core, and that's how the energy is generated. The technology is only really feasible if you manage the corrosion, because both natrium hydroxide and also the fuel salt are corrosive materials. So having steel tubes and a steel casing with very, very corrosive materials around them requires a strong corrosion control. So that comes both in form of material selection and material pre-treatment, but very much so also chemistry control throughout the operational lifetime of the unit. And that is where Seaborg is building our IP and patent portfolio is within the management of the corrosion. That is utilized both in our nuclear power company called Seaborg, but actually we have also founded a storage company which utilizes natrium hydroxide and our chemistry control to make use of natrium hydroxide as a thermal storage medium. So our company has a sister company called HIMNI, but Seaborg is the nuclear application where natrium hydroxide is the moderator within the reactor core. In a relatively simple schematics, this is how the energy is converted from fission to electricity. So starting on the left, you have the reactor core, where you can see the lighter green color, that's the fuel salt, so the salt containing uranium. That is circulated through the reactor core, where the moderator is present. So circulating through the fuel tubes, the fission product will reach a critical level in there, or will remain critical, and will have energy created from fission. That energy is transferred through the fuel salt, which is pumped outside of the reactor core into a primary heat exchanger, where the heat is transferred from the fuel salt to a secondary salt with no uranium. So this is a non-radioactive salt, which then transfers the heat again through a steam generator to water, so that we are creating high temperature, high pressure steam in a non-activated steam source, which can drive a steam turbine. The concept of a dual salt loop is not unique to Seaborg. That is something most of our molten salt competitors are also doing. And all of us are benefiting from the ability of salt to become very, very hot. And therefore, we can depend on the steam temperatures in a range above 500 degrees centigrade, which again allows for a very efficient utilization of the steam turbine, and overall having a good efficiency from fission to electricity. On the left-hand side, it is an arrow down to something called a drain tank. This is a safety feature also utilized all the way back in the Oak Ridge experiments. The concept is that should the fission process for some reason not behave as expected, the fuel salt can be drained into a so-called drain tank, which is a large vessel with no moderator. So in that vessel, the fuel salt will not be able to sustain a critical nuclear process or fission process, and therefore it will, over time, automatically cool. That drain tank is passively cooled with water. So it's a very efficient and effective safety feature, where should anything go wrong, you can, by passive means, drain the fuel into a vessel where it will cool over time, leaving very little need for operator interference and very low likelihood of uncontrolled incidents. In a little more lifelike schematic, this is how we envision our product will look. So starting on the left, 200 megawatt barge structure. It will come with two ready reactors upon first delivery. This is shown on the right-hand side of the barge, where it says 2 CMSRs, so compact molten salt reactors. The two reactors will deliver energy or heat, hot salt, to a steam generator, which again will run the turbine, which delivers electricity that is then via the high voltage equipment transported to the electricity grid of the location where the barge is located. Our reactor cores are designed to last for 12 years, and the fuel is enriched to a level where it can run continuously for 12 years. After those 12 years, the fuel salt will be drained to the drain tank, and the reactor will cool down. In the meantime, 2 new reactors will be delivered to the vessel and will be inserted in these 2 empty compartments already existing when the barge is delivered in the first place. And those 2 new reactors will then be commissioned and run for another 12 years, so that the barge overall has a 24 years operational lifetime. When you then look at the top right-hand corner of the slide, here you can see the vessel shown from the side, and here the concept of that power module, where you have 2 reactors and 2 empty compartments, steam turbine and everything. That module can then just be replicated, so up to the 800 megawatt unit, where then you would have 4 such power modules. The concept is that it's a very standardized and modularized system, so that scaling from 2 to 800 megawatts is relatively simple, but also that a 200 megawatt unit is economically very viable. In the bottom right-hand corner, you have a cross-section of the power barge around the reactor modules. So here you can see the reactor modules inside a steel casing, which is also the shielding of the irradiation, which means that only the steel casing containing the reactor and the reactor core itself will be the activated materials. Around the steel casing, we have water as part of that passive cooling system we have, but also part of the safety protection of the vessel. And then you have a steel hull, as you know it. Our envisioned way of delivering this technology is to, as mentioned, work together with Samsung Heavy Industries and Korea Hydro and Nuclear Power. We will design and develop the nuclear reactor itself, the compact molten salt, out of our offices in Denmark, but also together with our colleagues in Korea. The reactors are likely to be built somewhere in Scandinavia, then transported to Korea, where we are having an agreement with Samsung to at least build the initial barges in their facilities, install the reactors, commission the nuclear power barges outside of the Samsung facilities in Korea. Once tested and commissioned, they will be towed to the site where they will be delivering the electricity for the 24 years of lifetime. This is a highly scalable model and will benefit all of the receiving countries with the scale economies immediately, which of course is a big part of bringing nuclear to the market, is that it's priced at reasonable cost early on. Another benefit of having a long-term relationship with a shipyard partner like Samsung is that we can ensure very high predictability, both in terms of cost and schedule and quality, which are 3 main features for nuclear power. But we also believe that the maritime approach solves another challenge than just cost, reliability, and quality. It also allows for a zero production that the conventional nuclear power industry can probably not achieve. the point is that every nuclear power plant has to go through a very, very long and complex licensing process. And we believe that the maritime application allows for an alternative approach. And this is the model that we have developed. So to explain it relatively quickly, on the top left-hand corner, you have the UN institutions, so the International Maritime Organization, the IMO. This is the organization that today oversees all vessels traveling across countries. Almost every ship in the world is abiding to the IMO rules and regulations. Another super important entity in the nuclear aspect is, of course, the International Atomic Energy Agency, also governed by the UN. They, as you probably all are aware, provide the guidelines under which the nuclear industry globally is acting. Our proposed method of the maritime application is to take the rules and regulations from the IMO and the guidelines from IAEA and include them in our development of our technology and our products, so the power barge, including the nuclear reactor, and then utilizing the American Bureau of Shipping in our case, but it could be Lloyd's Register or DNV or one of the other classification societies as the third party and independent body to validate our design and the safetiness of our product. That is something the ABS or the classification societies have done in the past also. Actually, classification societies have in the past classified the hangar carriers or the flight carriers in the American military fleet and nuclear submarines, but they are also used in some cases for inspections of conventional nuclear power plants. So nuclear is not new to them, and they are today the ones classifying all vessels that travels the international waters. So these, we believe, are very competent and relevant bodies to involve in the nuclear industry for the purpose of allowing a large-scale rollout of nuclear. The way it works in the maritime industry is that the ABS validates a technology and a design, approves it, and confirms that it's safe for use. And then a flag state flags the vessel. So that could be Indonesia, it could be Singapore, or the UK. And that flag state is responsible for overseeing that the vessel continuously lives up to the classification requirements. So they are the responsible authority to validate the seaworthiness of the vessel and the abidance to rules and regulations as it should be. So following this process, we believe we can bring a nuclear power barge to the market that is already from the shipyard safe for installation and operations. Of course, that power barge will also, over its lifetime, be subject to safeguard inspections by the IAEA and all other inspections and aspects that conventional nuclear power plants are subject to. In that sense, we are still a nuclear power plant. We've just made it easier for the regulators to bring it to the market. And that's what is on the right-hand side of this. So, of course, there will still be a local authority in Indonesia. Bapeten will still be the authority regulating the power barge should that be deployed in Indonesia. And they will have their local rules and regulations that the power barge will have to live up to. Of course, that is to a large degree, it will be built on the IAEA guidelines, but any local regulations would, of course, still be valid for a power barge, should that be installed in Indonesian waters. A proposal of ours is we are developing projects in many geographies around the world, some of them in countries where there are already competent nuclear regulators, so countries who have had a nuclear industry for many years. And we are developing partnerships where these competent regulators can work as sparring partners for example, Indonesia, bringing the knowledge of how they have implemented both the floating concept, but also the advanced reactor regulations into their already established regulations, so that, for example, Indonesia can learn from these experiences and expectedly get to a competent level and ready for deployment of a nuclear barge quicker than they would otherwise have been able to. So in combination, the already or pre-validated design concept by the ABS and flag state setup, and the relatively lesser scope of the local regulator, since the product has already been reviewed by ABS, we believe will allow for a faster time to market of nuclear power barges than conventional nuclear power plants. This method, it should be said, or this approach, we are of course not just developing on our own. As said, we are developing it together with competent authorities around the world, both in the UK and in South Korea, for example. But we are also in close dialogue with the IAEA, because such a concept can, of course, not be developed without getting their input to the validity of it. Seaborg made a presentation to the IAEA forum a couple of months back, explaining this exact licensing model, and that was received very positively. So we are confident that we can find a way where this will be doable in a way where both the international society and the local regulators will be satisfied. And overall, of course, we have no intention of cutting corners or exploring gray zones. The barge should be implemented in a safe and prudent manner. That is for sure. A quick slide on the ABS, in the case that you are not familiar with them, but as said, it's called the American Bureau of Shipping, and it is a so-called classification society. They are having 5,500 employees and have a long track record in both the maritime space, classifying vessels of all types and sorts, and for all kinds of purposes. And they, as mentioned, are also active in the nuclear industry already. So we believe that they are a very competent partner overseeing our design, and ultimately they will be the ones issuing a new technology qualification for us. The process with the American Bureau of Shipping has already been started. So the first step was that Seaborg back in 2020, so 2 years back, submitted the conceptual design for the compact molten salt reactor, and the American Bureau of Shipping issued a so-called feasibility approval. That's a very initial starting step, but saying that this is sufficiently well thought through to start the qualification process of this nuclear technology. In parallel, we are of course also making a barge design, and with all the ancillary and auxiliary systems that should be on that, and that is also going through the approval process together with ABS. The timeline in very big steps is that we are developing this concept towards 2024, where we expect to start our prototype or our first unit production, which should allow us for a start of reactor testing around 2026. And we hope to obtain a type approval both from the American Bureau of Shipping, but also from the regulator that we will ultimately develop the nuclear reactor together with, and we will hope to obtain that in 2028, after which large-scale commercial deployment can be done. Yeah. And with that, we of course hope to commercialize this in the end 20s and start 30s. And to do that, we have already started the commercial development also, hence my role in the company. So the intention is that Seaborg, together with our consortium partners, in this case Samsung and Korea Hydro and Nuclear Power, but others might join, will take an active role in developing nuclear power projects, so that there are projects in plural ready to offtake the nuclear power barges as they are being produced. This is we are starting our commercial efforts in Southeast Asia because of the relatively poor conditions for alternative or zero emission renewable sources such as wind and solar, but also because that is a good fit with the Korean production facilities. So what we are already doing is that we're looking for local partners in this region who will and shall help us finding the relevant sites and going through the licensing process in the countries. Seaborg and our consortium partners will of course have a large role in doing the site evaluations and all the studies required to get the licensing and permitting done for the projects. And ultimately, we will also have a leading role in the construction process and in the financing of these projects. We're doing this work across multiple geographies for several reasons. The primary one actually being that we want to build scale immediately. So having multiple projects will allow us to reap scale economies from the very beginning. An additional benefit is that we will learn from different countries, which will allow us to bring learnings from, for example, the Philippines, Korea, Japan, Vietnam, to Indonesia, and the other way around, from Indonesia and back to those countries. We think that that is the fastest way to get everybody ready and comfortable with this maritime deployment approach of advanced nuclear reactors. To make this all feasible, I've listed a couple of key enablers that we rely on as a developer of these projects. Of course, we need to develop a licensing framework. To that, we need to engage with the regulators and the authorities of the countries to find a way where the regulations can be made ready for floating nuclear power. That is a challenge in all markets that we are engaged with. Even the current nuclear competent regulators are challenged with both the concept of advanced nuclear reactors, so the molten salt aspect, but also the floating dimension of our deployment. So this is a development effort that we are making everywhere. Then a second aspect is that to speed up things, we believe that there should be a framework for proposing nuclear power projects. So instead of everything being state-led, we would like that developers like Seaborg can develop a project, prove the suitability of a site, prove the interest in the society of getting nuclear power in a particular location, and the relevance from a grid point of view, and then engage in a direct dialogue with the authorities around enabling that nuclear power project. And part of that dialogue is also to engage in direct dialogue around PPA-like structures, where the revenue side of a nuclear power project has some certainty to it, because that is a key stepping stone to achieving a lower cost of capital, so attractive financing for the projects, which ultimately is a key enabler for low electricity prices to the consumers. So licensing, a framework for proposing projects, and then a state-backed power purchasing mechanism. Those are three vital elements for the successful rollout of new nuclear power on barges. And with that, I've come to the end of what I had prepared to present, and but I will of course be very, very happy to engage in a dialogue from here.
Thank you, Nikolai. So interesting. Well, Dear participant, if you have any questions to Nikolai, please raise your hand. You can ask directly to him. Among these more than 280 participants, you can ask. But first, I want to ask you, Nikolai. Usually, maybe you have frequently asked questions from the Indonesian people. Usually, there are three main questions from Indonesia. First, they will say, "Oh, this is very interesting," but we will follow other countries that they will first build and operate this power plant. Then after that, we will. How about this? How about to answer this question? The second thing is, maybe some of the participants already asked in the chat box, how much is the cost? I saw in the YouTube the Seaborg founder. Well, even he said much cheaper than coal power plant. This is not only to disrupt the nuclear energy, but also to disrupt the energy business. This is the second questions. And the third question, this is very familiar also. Our country suffering natural disaster like tsunami, for example. While you are offering the floating or barge on the top of barge, there is power plant. How about that situation? How to solve that kind of challenge in your technology? First, please respond these three questions.
Yes, so I'll reply, and please remind me of the ones that I might forget of the questions. But so if we start with this concept of nobody wants the first one, that is that is something we've heard many times and something we hear everywhere. And that's also part of the reason why we are engaging in multiple countries simultaneously. That is to build a portfolio of projects where all project partners can look, and all the nation states that we're engaging with can see that they are not the only ones involving projects together with Seaborg. But then, of course, there's always somebody who has to take the first one. Our intended method, as I also hinted to in the rollout plan, is that the first barge will be built in Korea, and that we'll actually have it situated in a test site in Korea to prove that it runs, and that is part of the approval process in Korea and part of the ABS qualification process. So we will have it operational for expectedly a couple of years in Korea before we get our type approval. At that stage, we do believe that somebody would be willing to take that barge and have that towed to their site once proven successfully in operations and safe to use. That is, of course, a process of developing the projects, but it becomes a little bit of a chicken and an egg, because first we need to get some projects where we can actually get to that level of dialogue. But that is what we're doing. So but there are needs, and I'm confident that timing and the continued pressure from global warming will mean that there are some who want to be early adopters of the technology simply because the world needs it. If it will be Korea, Japan, Indonesia, Vietnam, Philippines, let's see, that's still to be solved. But the intention is that to have multiple deliveries in the first couple of years after the first has proven viable. So it might not be that Indonesia gets the first, but then we are hopeful that you will get the second or third or fourth in the years following the first. So that's the one aspect. So that's the rollout, if you will, and let's see it work before we want one. We definitely aim for a model where we say it's conditional of the first working. Do you want to sign up for the second? That would, because that would give us a lot of transparency to the build out if we can make such agreements with countries and partners. So that is definitely a need. And then maybe I forgot your second question, but I remember your third, which is to the another very frequently asked question: the price level of these units. And it goes probably almost without saying that the first is going to be more costly than the 10th. That's how it is for every technology. There is a learning curve. And because it's nuclear, we'll also invest substantial amount of money in ensuring the safety of the first units. And as we get confident with the production methods and the performance of the technology, we can probably scale down on some of the QA and QC processes. Of course, still ensuring a safe product, but with a little less oversight. And all of that combined with the lower risk profile of the technology will allow for a significant cost out. That is how it is for every technology. So it is hard to say at this stage exactly what the cost level will be of the first unit, because a lot of that depends on the financing that we can attract. But we can also do the math and see that our long-term potential is in the range of between $50 and $60 per megawatt hour delivered. That I am very aware is not the lowest electricity cost promised by neither the nuclear technology or the renewables. But I think many of those who promise something that is substantially lower than that are either leaving part of the cost picture out. So, for example, solar, forgetting that they're intermittent and have to balance it to when it's actually needed, which will tremendously increase the utilized cost of solar power, for example. And I think some of our nuclear competitors are still in the very early stages of their cost calculations. So I think our estimate is both realistic and pretty well developed, but it's also not one that we will see from the first batch. The first couple of batches will need an extra commitment from the off-takers to enable the development of the technology.
Okay. So the third question is about well, we have an experience to use the Turkish ships.
Yes.
Well, using the gas power plant on the ship, and
Yes.
we distribute the electricity in some remote areas.
Yes.
I think it's very expensive, as long as I know. So maybe that's why some people are wondering, or maybe we can use the floating NPP to replace that kind of gas and power plant that we lend from the Turkey. But anyway, as far as I know, this is first of its kind. It's very difficult to calculate in a detail how much it takes to build this, for example, 100 megawatt electricity of Seaborg.
Yes. But I think, yes, and there is uncertainty as to the first unit's cost, but I am very confident in saying that we will beat these fossil fuel batches. They are very costly units. Similarly, the two-stroke engines running on diesel, providing energy to some of the smaller island societies in Indonesia also, they are also significantly more costly than the Seaborg batch. And actually, frankly, also, if you were to consider large-scale offshore wind farms in Indonesia, even the second power batch Seaborg delivers will be at a cost that is lower than those offshore wind farms. That I'm also very comfortable assuming. So we are not in the. I mean, we will be probably over $100 for the first of a kind, but we are not over 200. And today, many of these flexible energy sources that you're mentioning, they are running at LCOEs in that level.
Okay.
How about and then your second question, now I remembered, that was to the natural disaster risk profile of it. And that is, of course, it is part of the safety case that we need to develop for the product, is to prove that it's also safe in those conditions. The good starting point we have is that one of the risks for nuclear power plants around the world is the seismic activity, and in particular in this region. And there, due to being on water, we are not really impacted by seismic activity. So that's a good start. then of course we are more exposed to tsunamis because we are in the water where the tsunamis will come. And there are two mitigating actions that we need to look at. One, of course, is to situate the barge in an area which is less exposed to tsunamis. There you can look at historical maps and you can do probability assessments of where the tsunamis will have the highest impact. Mm-hmm. And the second thing that we will be doing for all projects is we will have to build a pier, so an artificial protection with a breakwater and then a mooring system. So something that can fix the power barge to the location where it is deployed. And that mooring system we are designing to be able to withstand tsunamis and hurricanes for that matter. So we are doing what we have to do to ensure that both tsunamis and hurricanes will not impact the safety of the power unit.
Okay, well, okay, thank you. Well, my next question is maybe I expect that several people from Torcon participate in this webinar. Some of them are Indonesian Nuclear Society members. Torcon it's very, very marketable. People love that kind of promotion. The thorium power plant.
Yes.
Although originally molten salt reactors. My question to you, how about the use of thorium? Is there any roadmap in your technology to use the thorium as the fuel for the future?
Yes. And that is also a frequent question. And actually, Seaborg was founded on an idea of using a thorium reactor. And again, back to the molten salt being very appropriate for thorium reactors. As we see it, and Torcon are free to disagree, but our main objective is to bring a nuclear power barge to the market as quickly as possible. Mm-hmm. And when we look at the current regulations and the current supply chain for nuclear fuels, we see that the thorium would be an added new element. So we are already with an advanced nuclear reactor. We are already utilizing a maritime deployment method. And we think that is sufficiently a stretch to the regulation that needs to be deployed. So we would like to bring that product to the market first, the one utilizing uranium in the molten salt, because then we are building on a known supply chain for uranium and the regulation regulating uranium reactors. Then we definitely see thorium as a great fuel, both in terms of the economics of it and the availability of it and the potential economics of it. But that is something that will come, in our view, several years later. So, but other than that, actually, we believe that our reactor can, not easily, but at least feasibly be redesigned to a thorium reactor, utilizing the same concept of molten salt and potentially also the natrium hydroxide as the moderator in such a thorium reactor. So we definitely see the potential, but we also think that that is something that will be, whereas we hope to deploy the molten salt reactor concept in the early 30s, then probably our to come thorium concept will be in the early mid 40s. Okay, so it means you are first to deploy using the uranium, then after that maybe 2050s or other several decades you want to use the thorium as the fuel. Okay. Yes, so that is definitely something to be explored. Yes. Okay, thank you. This is a question from Brin from National Research and Innovation Agency. They always ask to the vendors in which kind of activity that Brin as a research agency can be involved in this kind of development, because in their perceptions, although I'm in Brin also, if the vendors coming to us just to sell a technology, so Brin cannot be involved in that business. How about your opinion? Because national participation is very important for the government. Yes, and there was also a comment in your introduction as to the local content, or there was actually Paxulo Susilo's introduction that local content is important. And of course, national involvement is important. So if we start with the role of BRIN, we would very much like to engage and develop jointly, both to develop the competencies of BRIN and other similar institutions in the other countries we are, but also for us to learn and to grow confidence in the countries. That said, there is a limitation to how much we can co-develop the technology, because we need to be a commercial organization still that can freely deploy this technology around the world. So we are hesitant to engage in collaborations with research institutes around the world, which will limit our operational freedom. And that is continuously a challenging balance to find. That said, I think for BRIN in particular, and you are aware of that, Jared, that we have proposed, and we think that there's a very meaningful collaboration to be had in Indonesia around the fuel supply chain.
Okay.
Our reactor will rely on the so-called HALEU, so high assay, low enrichment uranium. That is to a large degree building on a known uranium supply chain, but it still has novelties to it, both in the production of the HALEU, but also in the decommissioning cycle, which of course comes 30 years after starting up the reactor, but is still something very important to consider. Not least if we want to develop the reprocessing of these HALEU fuels, which is something the industry as a whole is pushing for, because that can be very meaningful for the uranium supply chain. So long story short, we really want to engage with BRIN. We see that also a number of elements outside of the core reactor technology is something where we can truly collaborate, but we would also be very happy to engage around the core technology, because we see that that's an important aspect to actually understanding our technology and for example, Indonesia to become comfortable with our technology.
Okay, thank you. There is
and maybe
question.
Should I attach a couple of questions to, or comments to the local content aspect, because that is something that is, of course, with our primary concept of producing it in South Korea, there is a limitation to the flexibility to picking shipyards, at least in the early years of our rollout. We believe that is still in the interest of Indonesia, because the electricity prices will be lower doing that. Not because Korea is cheaper, but simply because the risk profile of the projects would be so much lower that it will attract a different kind of financing than if we were to invent a new primary supply chain every time. Of course, that is just a bar structure. And as I said, there is the pier, the mooring system, and there will be a number of hinterland or onshore facilities, for example, electricity or onshore substation for electricity transmission, but probably also warehouses and operational quarters and so on. And all of these things are large local content opportunities, not to mention the ongoing operations of the barge, which will of course also rely on competent local staff. So we see a lot of employment opportunities in the long run around these nuclear projects, but there will be, at least in the early years, a lesser local opportunity for the construction aspect of the barge itself.
Okay. Well, I think because some people inside BRIN, if it is already business to business, it is not the BRIN involvement, but the Ministry of Energy and Mineral Resources activities. But anyway, there is a good question from the head of Nuclear Engineering Department of Gajah Mada University. Pak Alexander Agung, would you please open your video and ask directly to Nikolai? Pak Alex? Please, Pak Alex.
Yes, hello. I'm sorry, I cannot open up the video.
Please, you have several questions.
Yes. In fact, I have, as I wrote in the chat box, the first question is, as far as I know, that Denmark is not a nuclear country. You don't operate a nuclear power plant in Denmark. So I'm curious whether you are considering to build and operate Seaborg FNPP in Denmark. And then my second question is, you are building a FNPP with liquid or molten type of fuel, and my concern is probably related to the seaweed, whether the seaweed will affect any power generation in the reactor or not. In solid fuel nuclear power plant or floating nuclear power plant like KLT40S, the effect is not so significant. Probably in the power, I mean in the steam generation, but not in the reactor itself. But in the reactor, for the Seaborg reactor, the fuel is liquid, and it also some kind of the it acts also as coolant. So maybe the seaweed would affect quite significant in the power generation. That's my questions, Pak Jarod.
Okay, thank you. Okay, please, Nikolai.
Yeah, thank you very much, Pak Alexander. So starting with the Danish non-nuclear aspect, and that is correct. Denmark does not have an operational nuclear reactor, and are likely not to have one in the foreseeable future. So the Danish nuclear regulator is non-existing, and there is a long pathway for Denmark to become a competent nuclear country. And therefore, it's not Seaborg's strategy to target Denmark as an early deployment country, simply because waiting for the regulators would delay our commercialization too much. And that is also the reason why we are working so closely together with the Korean authorities, and we are partnering strongly in Korea, because we see Korea is a much better country for developing our technology. It's a little bit of a coincidence that our founders were nuclear engineers living in Denmark, being born and raised in Denmark. But they are, so we are founded in Denmark, but the technology is very much developed together with authorities outside of Denmark, simply because of the lack of competence in the Danish authorities with regards to nuclear. Then we are building on a lot of other advantages in Denmark, and that is both, as was mentioned in the beginning, Denmark's history of developing high-tech technologies, but also in the renewable build-out. So we believe that there's a lot of benefits working together with the Danish authorities around the model for implementing new technologies in this renewable transition. So that's the story around Denmark. Our neighboring countries such as Norway, Sweden, and the UK and Germany, for that matter, they are of course long-time nuclear operators, and we are working closely together with universities and research institutions in those countries, because there we have the experience we need to develop our technology. And then to the aspect of the seaweed and our molten salt reactor. So the salt itself, there is no, and I think that's a very important point, there is no water inside our reactor core. The liquid state of the salt comes solely from heating the salt. So the salt is a rock at temperatures below 400 degrees, and above 500 degrees, it liquefies just because of the heat. So it's the salt structure that is suddenly becoming liquid. And then it stays liquid for 1,000 degrees more heating. So it's not water creating the liquefaction. And that is very important, actually, for two reasons. A, that means that there is no buildup of pressure because there's no boiling water inside of our reactor. And the other important aspect is that once back to rock nature state, so if the fuel salt is cooled below 500 degrees and it solidifies again as a rock, that rock can actually not be dissolved or has a very, very low solubility in water. So even if you dump our fuel salt into water, then it will stay as a large rock in the water and will not be dissolved, which is important in the safety case, because that means that the fission products inside that salt will also stay inside the salt because it is not dissolved in water. So that, I think, is a very fundamental aspect of a molten salt reactor. That is not water that makes the salt liquid. It is the heating of salt. So it's the salt itself. So that's one aspect. And then as to the seaweed and the impact on cooling, of course, there will still be a need for cooling. After the steam, we have a closed steam cycle. So that means that the steam after driving the steam turbine will need to be cooled so it can go back into the boiler, that water, and that requires cooling. And for that, we will need the sea as any other nuclear power plant with proximity to the sea. And there we will, but there we will have the same challenges as any other conventional nuclear power plant, in the sense of having a need to pump cool water close to our cooling system and pump hot water from the cooling system out to somewhere where it has little environmental harm. But there we will rely on technologies similar to that is applied on thermal power plants of any type and nature. And they have dealt with the seaweed issue in the past, and we will deal with it in the same way. The important part is, of course, the environmental impact of that hot water, but that is part of the environmental impact assessment that will be performed for every project.
Okay. Alex, do you have another questions?
Well, I think it's enough, Pak Jarod. Pak Somike, Nikolai, thanks.
Thank you.
Thank you. Well, there is one question from Pak David Yakubus about what kind of waste created by the Seaborg nuclear power. Is there the same with like a pressurized water reactor or other nuclear power plants types? This is maybe the fourth questions that always be asked by the Indonesian audience, because they are afraid with the waste, radioactive waste, and something like that.
So it's the waste that is the question, Jared? It's related to the waste, correct?
Yeah. Yes.
So every nuclear power plant will have fission products. So out of the nuclear process, you'll have a waste, and that is unavoidable. What is for molten salt reactors, all of that waste will be well contained within the salt, and then after that, salt can be considered spent fuel, as you would do it today in a conventional nuclear power plant. But the molten salt industry, we are jointly working to or pushing for a reprocessing industry to be formed, because the salt is actually a good medium for further reprocessing of the fuel. The point of reprocessing is that you can reduce the waste amount substantially. Some of that, which is today considered waste, is really not a problem to have inside the nuclear reactor. So some of those fission products that are existing in the salt could easily be reprocessed into a new fuel salt without having prohibiting effects on the new fuel salt. So it will not need to go to a deposit or be stored as waste. And then when you have, after reprocessing, you would have substantially reduced the waste amount. This is something that is proven in theory, and it has also actually been done at relatively large scale in the industry, but it is not something that is commercialized yet. So it's too early for us to go out and promise that this will happen and build on it, but it's definitely something that is, high on our agenda, and so with our colleagues in the molten salt industry, because this is something that is very near to all of our hearts, is to reduce the waste profile of nuclear. That is for sure.
Okay. Well, my imagination is because this floating power plant will operate about 12 years without refueling. So maybe the ships, if we want to operate in Indonesia, the ships coming from South Korea, then they are coming to us operating for about 12 years. Then after that, all of the spent fuel, including other radioactive waste, sent back to origin country. I don't know.
No, but, absolutely, and that's part of our thinking. So actually, one of the benefits of, we believe, of our design is that actually there will be no spent fuel handling during the operational lifetime. So in a conventional nuclear power plant, you will have spent fuel at the site during the operational lifetime that needs to be handled. Ours will be contained in the vessel. And actually the vessel will have a 24 years lifetime, because you'll have the first fuel cycle, but the first 2 reactors, they will stay on the barge when the second fuel cycle is operating. So you have 24 years without any spent fuel handling. And then, of course, after 24 years, we can all imagine what happens. As a starting point, the starting assumption will need to be that decommissioning takes place in the country where the barge is delivering the power. That is how nuclear power industries are working today. But as is known from Spain and France, for example, you can make a bilateral collaboration between countries as to the spent fuel handling.
Okay.
And it's definitely part, this reprocessing concept, that will make the most sense if you make some centralized locations where you do the reprocessing. They are probably expensive facilities to set up, and they're definitely facilities that needs to have a lot of safeguards, and there will probably be frequent inspections. So having centralized locations where the reprocessing can take place will be beneficial for the industry. And in the case that such a facility will be located outside of Indonesia, then yes, then we would take the spent fuel and tow that somewhere else and do the decommissioning there. Okay.
Yeah, because as long as I remember, several years ago, vendors from France offering us the flexible. They are using submarine technology. They said that the submarine will come to Indonesia. Then after several years, they go back to France for refueling and other things like that. So this is different, yeah. Okay.
But that can be done, and there are studies. Okay. Australia did a study a couple of years back looking into Australia being a host for nuclear waste because they have a lot of land and a very stable taxonomy continental plate that they are located on, and they estimate that that's a multi-billion US dollar industry to be a nuclear waste deposit country. So there is something that is already shaping up, but it's not well developed yet. That's the honest answer.
Okay. There is one question from Bapak Nathaniel Azar. You may ask directly, but I will read it. Who is the target of the Seaborg? Is it the unreachable area, remote area, some small island that lack of electricity, or most of its energy used for the industry? The question is for the area that lack of electricity for the industry.
Yeah, and of course we believe that our maritime approach is beneficial for island states like Indonesia or the Philippines, and there's a very obvious target use on these smaller islands which will need energy, and we think we are a very efficient way of supplying that energy to them. So that is definitely a target. But then also the large grids, actually, with an 800 megawatt electricity unit, we are also relevant for the grid on the Java Island, for example, the main use in Indonesia. We believe we can supplement renewable energy that might be built out there, so we can be the base load source for a grid like the Java grid. And we actually think 800 megawatt is a good size. It's large, it's very large, but it's not gigascale. So you could have 2-3 units connected to the grid on Java at different locations, and in that sense provide stability for the grid and a lot of energy. And then the last part, which is definitely also part of our scope, is the industrial application. there's both the option to use the heat directly. Of course, we can deliver heat at very, very high temperatures, good for mineral processing and industry at large. But also the very stable electricity output makes us an obvious fit with industrial applications using electricity, not least the emerging power-to-X industry, where we will allow for very efficient use of electrolyzers with our very high capacity factor.
Okay, because I saw also in your video in YouTube that the Seaborg also can be connected to the hydrogen production or water desalination or ammonia. Yeah,
absolutely, and that is definitely some of the use cases that we are exploring.
Okay. Other questions about the safety is sometimes when I observe the presentation from the Seaborg company, you are using the safety by the safety by physics versus safety by engineering. What does it mean?
Yeah, and that refers a lot to the salt and the properties of the salt. So conventional nuclear, of course, they have seen some, in particular in the 80s and 70s, some big disasters. Chernobyl as the one that is most known in Europe, where you had a blowout, quite simply. So the water in the reactor overheating and the reactor running amok, and then you had this release of steam, including fission products, which was very harmful to the surroundings. And that is the ultimate and the worst case scenario of a conventional nuclear power plant, and what has triggered a lot of engineering of safety mechanisms. So passive cooling, all kind of cooling systems, and remote shutdown opportunities of nuclear power plants. The lack of water, or the design where we have no water in our reactor core, means that this overheating of water and steam explosion cannot happen in our reactor. Therefore, we don't need to design for that scenario, because the water will not be there to do that. And the properties of salt, and it becomes technical, but the fuel salt that we're using will actually expand as it gets heated. So if the temperature of the reactor core starts increasing outside of the normal operational thermal spectrum, so let's say we have a maximum temperature in the reactor core, 700 degrees centigrade, for example. At 1,000 degrees, the salt will have increased so much in size that the fission product actually goes subcritical. So it simply means that the likelihood of hitting a new nuclear or uranium-235 atom is so low that the 3 neutrons released during fission will hit on average less than 1 new atom. So that the energy production will decrease once the heat, and that is called a negative temperature coefficient, and that is a common theme for all molten salt reactors. And that is simply because of the properties of the salt, and that is what we mean with the relying on. So this overheating scenario and meltdown cannot happen, because the salt can simply not facilitate a process where it runs amok. And that's what we call the safety by the laws of nature, or the properties of the salt, because it's not something we've engineered, it's simply just in the salt. And there are a couple of aspects like that built into our reactor design, where the properties of the salt, also this retention of the fission product in the salt, that is one of these things we don't need to design for a way of containing these fission products, because the salt chemistry itself solves that problem for us.
Okay. Well, it means that it will be simpler than the existing nuclear power technologies.
Absolutely.
Yeah, and
that's the main reason why we believe we can beat the cost of conventional nuclear significantly.
So the cost will be cheaper. Okay.
Yes.
And use it is where this is my imagination. It is very difficult for us, for example, to imagine that a ship that on that ship there is a nuclear power reactor, then they will through pass some international water, it's okay, but through some another country's area, in the past there were many anti-nuclear movement, the Greenpeace, even they have the ship and to protest. Do you think this kind of business will go smoothly with using the international water, or also the area in several countries?
So that's a very good question and a relevant point, and something that we are investing quite a lot of energy in exploring and looking at. So of course that is a case-by-case dependent question. So depending on where you want to tow your barge, you'll have different jurisdictions you need to pass through, and everyone is unique. But the broad answer is, first of all, the intention, or the one mitigating action, is that the barge will not be towed with reactors that are live and operational. The intention is that, or the process will be that after showing that it can go critical, so the commissioning in Korea, the fuel salt will be drained to these drain tanks. Mm-hmm. So that means that then you have a non-live reactor. So you actually have an empty reactor compartment and all the fuel in the fuel salt, or in the drain tank. And that drain tank will be comparable to a transportation casing in that sense. So it will not be a live reactor. That is one thing that will ease the transportation, because you are not transporting an active nuclear power plant. The second thing is then an active involvement with the nation states through which the barge will need to be towed. And I think that is something that is very important and where we need to engage. But it's also something that can be done, and it will be many years. Although I hope for very rapid commercial, very large success, it will still be a relatively low number of units that will be towed out due to the 24 years operational lifetime of each unit. And therefore it will be something that we need to handle case by case and follow very closely from Seaborg side. Of course, the great safety profile of our product is what we rely on in expecting that we will be allowed to tow through waters of nation states should that be necessary.
Okay, because I remember a long time ago when Australia sent their spent fuel to France. Then after they reprocessed in France, they carry the ships from France to Australia, the radioactive waste. Then there are many protests in some area, including in the international territory. But this is very interesting because, challenging for your technology when you want to use the shipyard, for example, from South Korea to Indonesia, for example. Some presentation by Seaborg said that using this technology, we want to avoid, it means you avoid the government involvement. It means this kind of business is going to B2B, because the technology is very safe. Then there's no need the involvement of the government. What do you think about that?
I think you found a relatively old presentation from Seaborg. That's the one thing. That is definitely not the position of Seaborg today. Okay. It's we believe that it is so safe that could probably be allowed, but that is after we have developed a thorium reactor. That is even later. I think the nuclear industry has a tremendous responsibility for acting in a safe and prudent manner. Mm-hmm. The accidents of the past have made the public afraid, and that has paused the nuclear industry for 50 or more years to the harm of the planet and the industry. And we are definitely of the understanding and the belief that we now need to rebuild our credibility. We believe we will bring a very, very safe product to the market, but that doesn't mean that we can act in in a reckless way. We need to abide to all rules and regulations that are relevant, and we need to win the confidence of the global community and the local communities.
Okay, yeah. Well, dear participant, is there any want to directly ask Nikolai? Or there are more than 300 participants today. This is a very interesting webinar. So some of the questions still trying to ask you about the safety. How about the potential? I think I already asked you. How about the potential disaster in Indonesia? Because we have a lot of tsunami, a lot of earthquake. Maybe again you can use the simple language to convey to the audience about.
So, starting with the earthquakes. So simply when you have an earthquake, it's the ground vibrating. That vibration is not translated directly through the water. So a vessel in the water is not affected by an earthquake, as long as it's not standing on the seabed, which ours will not be. So earthquakes that's one of the good benefits of being in the sea, is that the earthquake risk is negligible. What happens relatively often is that following an earthquake, a tsunami comes, or at least there's movement. If you have had large movements to the seabed, you also have large wave formations. And though that tsunami risk is something we are designing for when we build the mooring system, so the system to which the power barge will be fixated or fixed for the operational lifetime. So these are large steel or concrete pillars that will be put into the ground, to which you could tie the barge, to put it in simple language. And then there will be built a so-called breakwater, so a large pile of stones creating a hindering for the waves to hit the barge. And the combination of the hindering of the wave and the mooring system will make it safe to have a nuclear power barge there. And then probably imagination is a good thing. So you can easily imagine a wave so big that even the best mooring system and breakwater and everything fails, and then the power barge will be thrown to the shore, if you will, by that wave. But still, then the next level of safety features come in. The reactor core is inside the middle of the vessel, which has a strong steel structure, then some water protection, then a steel casing, and then you have the reactor. So you need tremendous forces to break into where the reactor is and to break that open. And then even if you imagine that happens, then what will happen is that this fuel salt will be released outside of the reactor vessel in the very worst scenario, after which it will be relatively quickly cooled to below the solidification point, and then the fuel salt will turn into a rock. A radioactive rock, but it will be a radioactive rock most likely still contained within that primary steel structure of the vessel. Which again means that from a environmental and societal accident point of view, it is not a catastrophe. Of course, I as an owner would be very sad to see my vessel on the shore and the reactor vessel broken, but it's an economic disaster, not a humanitarian catastrophe. And I think it's very important to distinguish between those two. Everybody can live with a company losing money. We don't want to be the company that have a negative impact on people's life, and we are very confident that is not where our technology will take us. We believe that we are safe even in very extreme environmental disaster scenarios.
Okay, well, very interesting. Another questions. Sometimes I always say to Torcon people, I hope Torcon people also participate in this webinar. If you want to build only one or two power reactors, it will not be sustained. It means you have to build many power plants. The first, I always say to them. And the second thing is the supply of chain. If we build very specific technology that there is no, the numbers are very small, so the supply of chain is challenging. even for the pressurized water reactor, because the material is very specific, so the high level quality of the materials. So my questions to you also, how about the challenge on the supply of chain, not only fuel supply, but also the materials? Because maybe you want to build one, two, and then another one, then you have to make a, well, like a chain, business chains that your technology will be sustainable. How about that?
That's a great question and very much into my core responsibility in Seaborg. So, and that is one of the reasons why, even though a country might not be the one buying the first power parts, we are very actively engaging in making a project that could be the third or fourth or fifth to build scale from the beginning. And that is definitely also to help develop the supply chain. And we are when we hit the long-term cost that I shared before, we are confident that this would be a large-scale success. And therefore, we are also engaging with countries, many countries, so that we can build a very large pipeline, as it's called, so a portfolio of projects lasting for many, many years with new builds. So that's the one part of it, simply creating some outlook to the demand so that we can develop the supply chain on that, to the extent the supply chain needs to be developed. And there are elements, particularly pertaining to the molten salt aspect, where the industry is still developing, and we're working closely together with suppliers to develop the tools and instrumentation and so on that we need for our product. And then the other aspect of that is that we are designing deliberately to utilize existing technologies as much as possible. So, for example, our steam turbine that we are assuming that we utilize, that is one that has specifications that are similar to what is used today in coal-fired thermal power plants. Mm-hmm. So that we are not asking for something unique. And that logic goes throughout. And really where we are building something that is very special to Seaborg is around the reactor core. And that will need to be built we will utilize to the greatest extent possible commercially available components. And there are that we can do to a large extent, but the assembly would be Seaborg unique. And there we will rely on our own portfolio of projects to get a sufficient scale. But in the big picture, that is a relatively small cost component. So the low scale economies in that aspect is not what will make the biggest impact on the levelized cost of electricity. There, the large hull structure, which will be built in a shipyard in dimensions that they're already familiar with, using methods they're already familiar with, that will be a large aspect. And then, of course, the fuel. And there we are also designing for utilizing fuel that is of similar properties and specifications as the general molten salt nuclear industry will be using. So there we are trying hard not to be too special for exactly the reasons you mentioned, that we don't want to be unique and we don't want to be suffering from the cost of one-offs.
Okay, well, one participant, his name is Yos, he asked, well, this is my first time to know that we have heard that Saudi Arabia built a big cruise ship, biggest ship in the world that ever before. Is it used nuclear floating too? This is the question from the audience. Do you know that about that information?
I'm unfortunately not aware of this particular ship. I would be very surprised if it has nuclear technology in it. If it's a cruise ship, I am aware of 3 commercial ships in the history of the planet who have used nuclear as the propulsion, and the latest was the MS Savannah, which only had a very, very little actual lifetime as a commercial vessel with nuclear as the propulsion. So I doubt that there is a nuclear propelled cruise ship.
Okay, well, another question. According your prediction, when this Seaborg will be built and operate, and what country? This is only your predictions.
Yeah. So the prediction is that by 2028, so the end 20s, we'll have a first reactor that is power barge that is operational. That is likely to take place in Korea at their test site, but it might also be in another country which we'll partner with. And as late as a little month ago, I was in Jakarta talking at the conference held there, where the possibilities of having a nuclear test site in Indonesia was also mentioned. And that is also something we are open to discuss. Should that be in the interest of Indonesia and make sense for our deployment? So a place, but it could also be a location in Europe. We cannot rule that out. That depends on the dialogue with different nation states over the coming years. But by 2028, we expect to have a first unit operational. And then after that, so immediately after validating the safe operations of the product, we want to deploy it. And it will not be 10 barges a year in the first years after, but maybe 1 or 2 barges per year following 2028. So 29, 30, 31, we expect to do something like that.
Okay. Yeah. Well, the situation in Europe is uncertain with the war between Russia and Ukraine. And do you think the people of Europe, for example, Denmark, will change their opinion about the nuclear, for example, because they have to use the baseload energy that maybe it cannot be depend only on the renewable energy? How about your opinion about it?
That is not only something I think, that is something we can read in the news every day, that the opinion is changing. So from Denmark specifically, there's been a very strong anti-nuclear movement since the 80s in Denmark. And this fall, for the first time since the Chernobyl accident, there was actually, in a poll that was made, there was a higher percentage of the population for nuclear in Denmark than against nuclear in Denmark. So the opinion in Denmark has shifted from a pretty strong anti-nuclear position 5 years back to now actually a majority favoring nuclear in Denmark. And if you then look around, so Sweden just committed, which is equivalent to $40 billion to new nuclear projects in Sweden. Germany extended the lifetime of their nuclear power stations that were supposed to be shut down by the end of this year. In the UK, there was just the other week the announcement of the Sesuai C, so the next nuclear power project where the government went in with a 50% stake together with the French EDF to develop a large conventional nuclear power station. Poland has announced some partnerships both with the company called NuScale, but also with Korea Hydro Nuclear Power to develop between 6 and 9 gigawatts of new nuclear in Poland. The Czech Republic just announced a new nuclear power station. France has gone out from we have all the nuclear we need position to say now they're also exploring new nuclear in France. So I think and Finland is also considering new nuclear. So there's really a very substantial shift in the mindset in Europe. And it's building on a very unfortunate situation in Ukraine and an energy situation which is very challenging in Europe as it is across the globe because the gas prices have been inflated as much as they have. But it's something that really, of course, is interesting from a commercial point of view for a company like Seaborg.
So yeah, so hopefully in the future, Denmark will change the policy of the energy. Do you think the government will change the policy? Well, this is the general questions.
Yeah. So my personal opinion is probably also built on hope, but I think they will. I think today we are seeing a very challenging situation for providing baseload, and that will not be lesser in the future. There are still 2 coal-fired power stations active in Denmark, which are due to be shut down. and wind will have a very high proportion in Denmark because we have very good wind conditions in Denmark for wind turbines, but they cannot provide baseload. That we've seen already this winter and fall. So they need to find something, and I think that it would make a lot of sense to get nuclear in as baseload in Denmark.
Okay, well, there is one question from the YouTube. Why don't you? Well, this is the person's he preferred to use online power plant. Is it possible to use this Seaborg technology online, not on the bar?
So technically, yes, you could.
Okay.
The reactor can work as well on land as it can being on a barge. But our commercial position is that we will be on a barge. We believe that it is much more efficient for large-scale rollout, both due to the licensing model, but also thanks to the serial production that we can achieve in shipyards. So we, like with the thorium reactor, there will be a future where we would also look at land deployment or onshore deployment, but we think that there are other people in the molten salt space who are probably a step ahead of us because that's their focus area, that is to make onshore deployment. And we believe that we are one step ahead of the competition on the floating deployment. And we believe that for Southeast Asia, for example, the floating approach is beneficial. Then, of course, if you want inland nuclear in the US, a barge would be inefficient or very difficult. And then we will leave that market to some of those who are primarily focusing on onshore deployment.
Okay. Well, I'm wondering about the fluorine salt. Some people always curious about this, the characteristic of fluorine salt, because still we have to study and analyze the influence of the salt to the materials that to be used for the reactors and other things. How about the study of the fluorine salt in Seaborg? Is there any progress that you can convince everyone that this salt is very safe?
It's a fundamental part of the safety case that we ultimately need to show for the reactor to have it licensed. So we agree that is a critical aspect. And that is something that we are then, of course, also working on now. So the vast majority of the employees in the Seaborg are of technical background, and we have 20 PhDs employed in the company, and a lot of the efforts that we are having or doing right now are going into our laboratories. So we have 3 different laboratories, and we have a large laboratory being built, and we have collaboration with a handful of universities around the globe. And all of these collaborations are around the corrosion, both of the natrium hydroxide, but also of the fluoride fuel salt. So looking at the corrosion of the salt itself at different temperatures and also under irradiation. And those are fundamental studies, and that will continue for the next, and even beyond the first commercial deployment, because that's an element of continuous development.
Okay, thank you. Well, we will be 6 p.m. So I want to ask you to have a closing remarks that if you have any, please, Nikolai.
Yeah, but I just want to say thank you so much for having me. Thank you for everybody to stay on until these relatively late hours in Indonesia. It's been a great pleasure, and I really am thankful for the many questions, good and relevant questions, and this opportunity to present Seaborg's view on these. We are very happy to engage. So if any of you should have questions afterwards or want to talk more, we are really welcome that you reach out, and then we can take the dialogue from there. And then, of course, we hope to have a prosperous future in Indonesia with many nuclear power barges delivering clean and affordable energy to Indonesia. So thank you very, very much to all of you for having me, and you in particular, Jared, for inviting me.
Thank you, Nikolai. Dear everyone, it's very interesting to hear the Seaborg technologies, because I believe Indonesia is a big country, the archipelago countries. Yes, we need pressurized water reactor. We need other technologies also, because some islands they need maybe the specific demand, and I believe that a lot of technologies, not only one or two molten salt reactors among of this kind of technology. And not only on that, the Seaborg also offering for the hydrogen production, water desalinations, because some of the state-owned company also want to study the application of nuclear power for that heat for the industries. But anyway, thank you, Nikolai. Hopefully, we can still communicate. Well, I'm still going to communicate with you, and we want to discuss more technical matters with BRIN, with other stakeholders in Indonesia, like with PLTN, with the universities. Then we can collaborate on this technology. Again, thank you very much. We will see you next time. Thank you.
Have a nice evening. Bye.
Terima kasih Bapak Ibu sekalian, bahwa sore ini kita sudah mendengarkan dari Pak Nikolai terkait teknologi mereka yang harus kita pelajari juga semangatnya. Denmark tidak punya PLTN tapi mampu menawarkan PLTN. Denmark, they don't have the nuclear power plant, but they have several startup companies to promote the nuclear power plant, including to Indonesia. So we can follow, even you are good engineers, kalau Bapak Ibu itu ahli di bidang reaktor, bisa mendesain reaktor, bisa membuat startup company. You can make Indonesian startup company, just like this Seaborg companies. Again, thank you very much. Terima kasih. Kita ketemu Kamis depan dengan topik yang berbeda, yaitu kaitan dengan tsunami early warning system. Ini bagian dari kita untuk selalu teringat bahwa Indonesia mengalami banyak kejadian natural disaster. Terima kasih, sampai ketemu. Thank you very much. See you next time. Thank you.
Terima kasih Pak Jarad. Thank you, Nikolai.
Terima kasih.
Thank
you, Nikolai.
Thank you, Mr. Nikolai.
Thank you very much.
Thank you.
Terima kasih.